Hello everyone, and welcome back to the Edmond Optics Imaging Lab. I'm your host, Nick Sischka. We've done a lot today with a whole bunch of different labs, and we've reached our finale. So we've talked all about F number, we've talked about color, we've talked about focal length, we've talked about field of view, and we've talked about megapixels. We've talked about a lot of different concepts. Now I want to introduce the final concept today, which is lateral and axial chromatic aberration. So in the last lab, we talked about F number and color. And we spent a lot of time going into how color can actually impact your overall lens performance from an absolute perspective. And we saw that as we went down in wavelength, we saw our performance actually increase. And now we want to take a look at other ways that color can impact a lens performance. And we're going to look at that and how that manifests in two different types of chromatic aberration. And in order to do that, I have got a FLIR camera set up here. This has the IMX 183 sensor in it. This is a 1-inch sensor with 2.4 micron pixels. I actually have taken this sensor and done an AOI on it. That's an area of interest to make this a 2/3-inch sensor. That's because the two lenses that I'm going to be using today, which are two 35mm focal length lenses, are both designed for a 2/3-inch sensor, but I wanted to take advantage of the small pixels that are in this, as well as some of the newer Sony Pregis technology. So I went ahead and just AOI'd that sensor there. And then I also have an RGB backlight. Now before I jump into the lab, I want to spend just a couple minutes doing some quick housekeeping in case you're just joining us. If you're just joining us now, we've done several different labs throughout the day. And I mentioned throughout those that this is not being done live. These have been pre-recorded, and this is the same case for this lab as well. I am doing these experiments real time, so if anything comes up that's kind of funky, I'll work through it, and I appreciate your patience there. It's part of the fun of doing the actual science real time here. Additionally, I am standing by online to answer any questions that you guys may have. So if any questions pop up during this, please feel free to type it in, and both myself and a team of expert engineers are there to help you answer any of the questions that you may have. So without further ado, let's go ahead and jump into this. So I mentioned that we were going to be talking about lateral and axial chromatic aberration. Well, what are those types of aberrations? What do they mean? We'll jump into that in a minute. But first, I'm actually going to hand this off to CCS Illumination to talk about some ways that you can actually create white light.
Hello everyone, my name is Lindsay Dragon. I'm an application engineer at CCS America. Today I'm going to be talking about the difference between creating white light with an RGB light versus using a true white color LED. And I'm also going to touch on a few other topics regarding the use of an RGB light in general. Before we discuss the differences, we need to know how color cameras recognize color. Just like in humans, color cameras have 3 sensors or channels, and each one is sensitive to only one primary color. So one channel is sensitive for red, one for green, and one for blue. The intensity ratio of these channels can finally represent the color. For example, a 1:1:1 ratio will appear as a white color. The same principle can be applied for LEDs. If we turn on a red light, a green light, and a blue light at the same intensity, the camera will still recognize it as a white color. And this is how we can create a white color with the composite RGB light. The downside of the composite RGB method is the spectrum. The composite RGB light has 3 peaks at red, green, and blue, so some wavelengths are lacking, such as orange and cyan. Versus the true light LED has a broad spectrum band that covers all of the visible wavelengths. The spectrum varies between each LED and LED type, and there are some LEDs we call natural white that have a full spectrum to imitate the sunlight for high color rendering index. Long story short, if your application is inspecting the true color, a true white LED or a natural white LED will be a better solution. RGB lights have other, arguably more useful features than creating just white light. To start, if you change the intensity from any of the ratios, you will get a new color. For example, having red at 100% and blue at 100%, you will get, and green at 0%, you will get more of a magenta color. RGB light is the most effective with monochrome cameras and is not very useful with color cameras. We use colored lights to enhance contrast in images, and if you have, for example, a red object and a blue object, and you shine a red light on that object with a color camera, you'll still see red and blue. The blue might look a little different, but with a monochrome camera, the red will appear very light and the blue will appear very dark, increasing the contrast. So we have samples that are the same shape but varying color. We can use different colors in the RGB light to create contrast and highlight features that we want to see. This is just a brief introduction. There's a lot more information to learn, such as using RGB lights to create high resolution, noise-free color images with a monochrome camera. I don't have time to go into details on this right now, but please reach out to CCS if you would like more information on that point or any of the points I mentioned today. Thanks very much.
Thank you so much. That was incredibly helpful information. And so now that we know a little bit about how RGB light forms white and stuff like that, I want to go into this demo a little bit further. So we can see with this light, right now I have it set to white, but because it's white, it's actually a composite white. And I can come in here and I can change the different colors, and I can do red, I can do green, and I can do blue, and I can do any mixture of those. Of course, if you combine all three, we wind up with white light. And so now let's explore how that can impact our lenses. So while CCS was talking, I actually went ahead and put on a 35mm lens here. This is a C-series lens from Edmund Optics, and I'm looking at the star target array, just like we're used to seeing from some of the other demos. And let's actually zoom in here and take a look at our performance in the center, because what I want to start us by looking at is axial chromatic aberration. And so axial chromatic aberration, kind of as the name implies, occurs on axis. And so what winds up happening in lenses is that as you have different wavelengths of light going through that lens, the lens will actually focus them differently. If anyone's ever seen the Dark Side of the Moon cover from Pink Floyd, or if you've ever worn glasses and looked up off into the corner, you've seen some of these colors bleeding and things like that. It's the same type of effect. And this manifests itself in lenses as well. And axial chromatic aberration essentially means that you have different focal lengths for the different wavelengths of light that are going through that lens. And it turns out that blue focal lengths are actually a little bit shorter than red focal lengths, because light is bent differently depending on the wavelength of color that's going through that lens. And so right now I have composite white light going into this lens, and I focused it for the white light in the center. And as I said earlier, I zoomed in here so that we can just see this central star. And I want to take a look at how a lens that's well corrected for this actually behaves. So I'm going to go ahead and start by looking at blue, which is our lower wavelength, and we can see our current performance with white light looks pretty good. We're almost all the way bottomed out on this target here, and I'm about 300 millimeters away from this glass target. So I'm going to go ahead and turn off my green and red channels here. And I see my performance changes a little bit from white. Maybe this blur circle got a little tiny bit larger, and that's fairly common for that to happen with some of the wavelengths. But you'll notice that the impact was not very large. This is still very, very good. I might be able to come in and very slightly tweak the focus in order to get that to look a little bit better. But let's take a look at the stability throughout the wavelength range. So if I turn off the blue and I turn on green, one other quick note here, I do have this camera set to an auto exposure. That's just to keep things looking as even as we can, because as I'm changing these dials on the wavelength, there might be some differences in intensity and stuff like that, not to mention the quantum efficiency of the sensor. But I also just want to make this look as even as possible for you guys. So with green, we see that there's very little difference as well. I'll go back to blue since I just decided to talk to you guys for a couple seconds here and see the difference. There's a very small difference. Maybe blue looks a hair worse. But the green here looks pretty good. And then if I go over to the red, we notice that it also still looks good. Right? We're seeing good performance across the board, irrespective of the wavelength of light that I've chosen. And if we go back to the white light, we still see really good performance. Now let's take a look at what happens with another lens as I thread this on. Now the lens that I'm going to be threading on here is not an Edmund Optics lens. It is a 35mm focal length lens, and it is designed for a 2/3 inch sensor. I have made sure to put this lens at f2.8, just like our last lens. So we have this here, and let this focal length balance out. Now don't look at the performance yet, I haven't focused it, so it's not quite fair yet, but let's go ahead and focus that out. This is about as good as the performance gets. It looks pretty decent, right? We're in the center. We would expect all lenses to look pretty good in the middle, and it looks pretty decent, right? There's nothing really wrong with the way this performance looks. Let's go ahead and do the same thing. Let's go ahead and step down starting with blue. We see our performance still looks pretty good. There was maybe a little bit of a change. Maybe this lens actually got a little bit better as we went to the blue wavelengths as opposed to the Edmund lens, which actually got a tiny little bit worse in the blue there. But let's see what happens when we go to the green. Still looks about the same. But now let's see what happens when we go to red. Look at this performance difference that happened here. Our chromatic aberration really increased. And I'm going to zoom in and take a look at some of these phenomena that we have going on here, because it's actually quite fun from an optics perspective what we have going on here. We can see if we follow, let me use my mouse here so you can see on the screen. If we follow this black line down and it goes into this blurry area, we're actually seeing it turn into a white and then go back to blurry and then go back to dark. Now that's actually something that's really fun and is a clear indicator of optical defocus, which actually is indicative of your optical transfer function going negative if anyone is an optics nerd here. But that's actually what's going on here. Now I can focus this back just with the monochromatic light and cause our performance to get a little bit better. Actually quite a bit better, but then the performance also starts to degrade with the other colors as well. And so really it becomes a trade-off game of how you're going to be balancing out the lens, and knowing that if you're going to have a source that has a large red component, this lens wouldn't necessarily be the right choice. And now I'm actually going to hand this over to Steven from FLIR, and he's going to talk a little bit about how color can impact a camera's performance.
Hello everyone, welcome to the quarantine edition of All About Colors. My name is Steven. I'm an applications engineer at FLIR Systems, and I work in the machine vision department. Here we specialize in high-end industrial cameras such as these, and they operate in the visible range. Now, Edmund Optics and FLIR, we have been partners for a very long time, and throughout the past, we worked hard together to provide excellent vision systems to our customers all around the globe. Now today I want to talk about color. Color we see everywhere. Every day we go outside, we see color. We look at our phones, we see color. And if you're active on Instagram, your phone camera sees a lot of color on a daily basis. But how do cameras see color? Today, most sensors are predominantly CMOS. There are millions of pixels that are there to capture photons. And when we group these pixels together into quadlets, that's how we arrange color. Let me show you how.
Now imagine this grid. This is your sensor. Every one of these rectangles is a pixel. We have a default Bayer pattern of RGGB. What does that mean? Red pixel here, double green pixel here, and blue pixel here. Now this is a 2x2, therefore it's a quadlet, meaning 4 pixels. If we continue on this pattern, in the first line you'll have red here, red here, red here, green here, green here, green here, green, 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 blue, blue, and blue. So for every quadlet, you have 1 red, 2 green, and 1 blue. Now quadlets are defined as each one of these 4s. That gives you the term RGGB. And you'll see that a lot in our cameras.
Now, let's talk about sensitivity. There are 2 parameters that we want to know: the absolute sensitivity threshold and the quantum efficiency. The absolute sensitivity threshold is the minimum number of photons that you would require to overcome a noise floor or to get a useful electrical signal. Quantum efficiency is the percentage of photons that hit the sensor, which then gets converted into a useful electrical signal. Both are important, and like our own eyes, CMOS sensors work the best in green light, so about 520 to 530 nanometers in wavelength. Now, you may be asking, what about white light? Well, if you ever played with a prism, you'll know that white light just contains all the colors, meaning even with white light, whatever green portion it has will be more prevalent in the camera. What about monochrome cameras? Well, monochrome cameras are still visible cameras. They operate between 400 and 700 nanometers, which is the visible range that we see. And whatever is green in there will be the most prevalent to the camera. Let me show you how through these charts.
Now let's take a look at the quantum efficiency plot of a color camera. As you can see, green has the highest quantum efficiency. Green also has the widest range. Therefore, as mentioned before, this color camera is the most prevalent when working with green. Now, if you take a camera and you grab the raw image off of the sensor without any white balance or color correction matrix, that image will appear a lot more green than what it's supposed to look like. And this is the exact reason why that is, due to its quantum efficiency and the wide range that it covers. Now, we fix these images by doing white balance and color correction to ensure that they have the right color space and all the colors are portrayed the way that your eyes will perceive them. Now this is done through a matrix, and there's a lot of math behind it. We do have lots of resources telling you how to do so, and I will encourage everyone to have a look at color correction and white balance if you have the interest. In older sensors, this peak quantum efficiency used to occur in the red range. This is no longer the case. The technology has shifted, and in CMOS sensors, this is now in the green. Now, let's take a look at the quantum efficiency of a monochrome camera. If you remember previously, color cameras have a very steep drop-off between 400 and 700 nanometers. Anything above that will no longer work. Why is that not the case for monochrome cameras? Well, for FLIR machine vision cameras, all color cameras have a IR filter. Now, this IR cutoff filter is integrated into the camera to ensure color cameras work correctly. Mono cameras, however, don't have this filter, hence the quantum efficiency does bleed into the NIR range. While not being the greatest NIR camera, anything above 700 to about 900 nanometers is still usable. Now, some customers do choose to use it in this range, and they have found very good results. Now, if we stick to the visible range, which is this region right here, you'll see that green is still the most prevalent. So despite the chroma, green is always going to be the most prevalent color when it comes to working with visible cameras. So right here, we have about 520 nanometers. And that's the optimal wavelength for the sensitivity of this camera, giving you the highest quantum efficiency. Now, this curve and the curve before are from the identical camera. They're the same model, and the only difference is their chroma, one being monochrome, one being color.
I hope we all learned something useful today. Remember, it's important to know the color space you're working with and the type of lighting you're providing when choosing a vision system. Not only will this affect the camera that you choose, it will also impact your optics. Different colored light do behave differently when they're passing through lenses. Luckily, at Edmond Optics, they have tons of experts that can answer all the questions you have regarding optics, lenses, and how to pair a camera with their lenses. Glass might be common, but the science behind it is quite deep. Thank you all for joining me today. Stay safe and have a great day.
Perfect. Thank you so much, Stephen. That was awesome to learn about some of the ways that camera technology has changed over time, and as well as how color can impact a sensor's performance. So now while Stephen was talking, I went ahead and made a couple little changes on this. I threaded our 35 millimeter lens back on here, and then I also tilted our target so that now we can see that we have a star up in the very far corner of our image here. And so what I want to actually do now is, instead of looking in the center where I was before, I'm going to zoom into our corner. Just going to go ahead and digitally zoom in there. Might actually just ever so slightly tweak this so that it's a little bit more in the corner. There we go. Actually, make sure I did that right. Yeah, we're looking good. All right, and this time I'm going to zoom really, really far into that corner. Because what I want to see is actually these individual pixels. And we can see them now, and I'm going to go ahead and put my mouse cursor right at kind of where the edge of our object is. It's probably around here. Now what I want to do is I'm going to step through our focus positions, and I'm going to take, our wavelengths, and see how our focus changes now. Because now I'm off axis, so we're expecting to see what's called lateral chromatic aberration. And lateral chromatic aberration is where you actually have different magnifications that come from your different wavelengths. And that happens because, again, your focal lengths are different, and so that creates the different sized images. And so you actually can have multiple images layered on top of one another that are being focused by the different wavelengths of light. And again, because we have composite RGB, what we really have here is a red, green, and blue image all overlaid on top of one another. And we have this now focused. So let's see what happens as I step through this, and I'm going to start with blue. And so you saw we actually did get a slight change, but it wasn't really a whole bunch. We maybe saw a half pixel shift or so. And now as I bump this up to green, and I eliminate my blue, we see there's a little bit of a change here. And now as I go to red, it does change back. And now there's not a huge change, but what we actually noticed was that we saw the biggest change not from blue to red, but actually from blue to green. And that's because this lens is designed to be what's called achromatic. And so that means that we've color corrected two different wavelengths, which are usually on the opposite ends of the visible spectrum, in this case red and blue, to actually coincide with the same focal length. And so if I go back to blue, there's no change, but if I go to green, that's where we actually see a very slight change downwards. And that's what we wind up seeing in a lens that is well color corrected. You'll always see some of this shift, but let's take a look at a lens that doesn't have good color correction. I'm going to switch this back to white. I'm going to thread this other 35mm lens on here. Okay, and I still have this set at f2.8. And I'm going to zoom into our corner again. About right here is where I'll put our cursor. Now again, I'm going to step down to blue. And we noticed a shift here. So I'm just going to go ahead and reposition my cursor where it was at the blue, so that we can get a good idea as we increase our wavelength how many pixels we're shifting. Because we saw from white, we saw about a 1 to 1.5 pixel shift. And if we go to green, here we see that pixel shift again about a pixel up. And now what happens when we go to red? We see a pretty substantial shift here. Now, there's also quite a bit of defocus going on within this individual star here. And so what happens as I focus this, let me go back to blue since I moved my mouse cursor. And I'll reset this here. And then I'm going to go back to red. Now I actually want to focus this lens now until this is as sharp as I can get it. And now we can really see how many pixels this has shifted over. And keeping in mind that each pixel here is 2.4 microns in size, we're seeing a pretty tremendous shift in the terms of the number of pixels. We're seeing about 5 to 6 pixels of shift away from where we originally were. And that can be a huge impact on a lot of different applications where you're using white light and you're trying to get as crisp of an image as possible. So color can impact lenses in tons of different ways. Lateral and axial color are your two large impactors. There's some other things that can creep in there from a higher order perspective. But for now, that's what I have for you guys. Thank you so much for joining me today in our Edmund Optics Imaging Lab. I've really had a lot of fun doing some of these labs with you guys and showing you some optical properties and how lenses work. Please feel free to reach out at any time for any questions. I'll be staying on as well. I hope you guys enjoyed. Thanks so much.